So as we started talking about last time, today we will do the following theorem. For graph H, the H removal lemma So in the notation we had yesterday, means that the delta in the removal lemma is polynomial in epsilon, and only if H is measured. So yesterday we explained why if H is bipartite, then the removal lemma is polynomial. So today we'll put the other direction. And first I want to do it for odd cycles. So I first want to show you the proof for odd cycles, and then there is another trick to get to any non-bipartite. But before that, we'll prove a lemma from combinatorics. Okay. We'll see how why we need this lemma. So let's say 3. There is subset of 1 up to n, which is quite big, so it has like n 1 minus 1. Such that if x going up to sk minus 1 is equal to k minus 1 times sk, or x1 to sk belonging to the set S, then actually this is only possible if all the x's are equal. Forward, this set does not have any non-trivial solution to this equation. Of course, if you take all the x's to be equal, then it's a solution, but this is what we call a trivial solution, and there are no others. Now observe that if we take k equals to 3, then we get the equation x1 plus x2 equals 2 times x3. So this is exactly a 3-term arithmetic progression. Right? Because this means that x3 is exactly in the middle of x1. In particular, this is a construction of a large set size almost linear. Of y, so n to the 1 minus 1, which doesn't have a strict arithmetic. And this is so this construction is stereo. Let's see the proof. So the first idea is that we will write n and p the power p, so we will choose p and p together. And we will represent each s in base p. That means that we can write f sum I from 0 to -1 AI times the I. So we just represent it in base t, and then we associate to x this vector of coefficients. So t -1 up to a. And the first thing we'll do, we'll look at the set of all x, such that all the coefficients a -1 of x up to a0 of x are at most strictly less than d over k. Yeah. D -1. Yeah. So why do we want that? Because sure, every x1 up to xk -1 in U, the vector of the sum of them is equal to the sum of the vectors. When you add up two numbers, in some base, say t, then what could happen is that you can have carries, right? And then this doesn't hold, right? So if you have, you sum digits, then you have to carry a 1 here. Then it's not true that the vector of the sum is just the sum of. But because we insist that all the digits are less than t -1 over k -1, you never get this carry, right? Because if we sum k -1 of these numbers, it's still at most t -1, so we do not get. Is this clear? Any questions? Okay, and similarly, if I take the vector of k -1 times xk, this is the same as taking the vector and then multiplying it by k -1 for every xk in U. So what this allows us to do is, instead of thinking of the numbers in U, we can instead think of the vectors. Because with respect to addition of up to k -1 terms, they behave the same way. Okay. So the second trick is that we will fix some R and say S should be the set of all vectors in U such that the norm, this is just Euclidean norm of V of S, is equal to R. So in other words, this S is a sphere. Well, it's the image, pre-image of the sphere. So why are we taking a sphere? Well, so suppose that x1 up to xk -1 satisfies this equation. We want to show that this is only possible if they're all equal. Layering S. And let's denote by vi, the vector of that kind, then we know that v1 to be k minus 1 is equal to k minus 1 times k. But observe that this means that vk is in the convex hull of this vector. Okay? It's actually their ever. So it's in their convex hull. But on a sphere, this is impossible. Right? You cannot take k minus 1 point on a sphere and take their average or anything in their convex hull and still be on this. Okay, so that's why we are taking it. So let's prove that this is impossible. So the way to do it is we'll take norms of both sides and we'll apply the Cauchy-Schwarz. Okay, so if we take norms, then the norm of k minus 1 times pk, this is just k minus 1 times r. And on the other hand, this is the norm of p1 pk minus 1. This is the smallest I'm using. No, square root of pi times square root of k minus. And the equality, this inequality, we also know that we have equality even though all of these k's are the same, the i's are the same. Now here we have, all of these numbers are r squared. We have k minus 1 times r squared, and we take the root, so we have another square root. So this is k minus 1 r. And so we actually do the equality. We see that both of the sides are equal. So we must have equality here, and that means that all of the i's are. The i's are the same. That this then means that all of the x are. Okay. Good. So the last thing we have to think about is what is the size of it. And here we'll just use pigeonhole. So we are free to choose R. So what we'll do, we'll see how many options we have for R, and then we'll divide by this number of options. So for every x in n, the norm of the vector of x is the smallest, so square root of p times p squared. Let me do it without the square root. This is the smallest p squared. So that means that the number of options for R the smallest t squared. Therefore, by pigeonhole, there exists some R with such that the size of X is at least the size of U. Remember that U are those where the digits are small. Have this restriction, and out of all of those, we divide by, we choose the best R, so we divide by 10. Okay, so what is the size of U? So this is something like B over K, right? So B minus 1 over K minus 1, the lower bound B over K, the power T over T B squared. And now B to the T is N, so I can write N. And here I have K to the T, T B squared. Now, I want to minimize this number, because I want the size of S to be as large as possible. What I'll do, I will choose, so this T is not really important because this K to the T is much bigger. So what I have to care about is K to the T and T squared. So I want these two numbers to be equal, and then I'll minimize. So let's choose T and D such that K to the T is equal to D. So this squared would not really play a role. Let's just say K to D. We also know that T to the T is N. So now we have two equations we can solve for T and T. Let's see what those are. So this means that K to the T squared is N. So T is square root log N over log K. And if we now plug this in, if we plug this in here, you can check that what we get is that S is N over E to something. So there is a constant here depending on K, and here we have square root of N. Because what we have here is K to the T. This is something like E to the square root of N. And we also chose the parameters such that this number is roughly equal to that number. We just have another function. Now this is N to the 1 minus integral. Any questions? Use this. So the next thing we'll do is prove this theorem for all sides. So we'll prove the following. So let's say there exists an n vertex B with epsilon n squared as disjoint copies K and no other K. So the only copies are this collection of edge disjoint copies. So we'll pick no other copies of K and the K 1 over epsilon to the omega of 1. So that means that n is bigger than any polynomial in one of n. If we actually see what we get, what this proof is, then it gives 1 over epsilon to omega of log 1. Or another way of writing this, e to the log squared of 1. Somehow this log squared exactly corresponds to the square root log n. If you invert the graph. Okay, so let's prove this. Okay, maybe before we prove this, this implies that the delta of pk is not polynomial, so it's smaller than any polynomial in epsilon. Because the number of, so if I take the number of pk in G and I divide it by n to the k, so this is the delta we're supposed to have, right? Then this is most, so all of these copies are joined, so I can have most squared of them. And here n to the k. So in particular, this is at most 1 over n. But n is bigger than this, so this is at most epsilon to 1 over 1. It may look a bit confusing because here n depends on epsilon, but in the removal lemma, epsilon is fixed and we let n grow. Right, but what's happening is that this theorem gives us this specific graph, and then we can also blow up this graph to get a construction for any n. So you can imagine that the fixed epsilon, we have the fixed graph, and where the removal lemma is this ratio is smaller than any polynomial in epsilon, and then we can take blocks of this graph and give us a construction for any number that shows that the delta in the removal lemma is smaller than this. Okay, so let me prove this theorem. So take S from the lemma. And we choose n such that size of S is epsilon times n. Now we know that S is n to the 1 minus integral of 1. Right? So if this is epsilon n, then this means that n, the literal of 1 over epsilon, so n is and 1 over epsilon to omega. You can also do it, you can do it more carefully by saying that the size of S is n over e to the constant log square n is the actual estimate you get from the lemma. And if you use this estimate instead of just general n to the 1 minus integral of 1, then you get n is e to the constant log square 1. Okay. So what do we do with this? And here's the construction. To take K set B1 up to Bk, and we identify each of the sets with the numbers from 1 up to Kn. So think of each of the sets as the numbers from 1 up to Kn. And then for every y in n, and for every x in our special set S, add a copy Bk on the vertices B1 up to Bk, where Vi is in Vi, so I'll draw it in. And Vi is equal to y times I minus 1 plus I minus 1. Let me draw this, then I think it will be clear. So we have V1, V2 to Bk, and we take the vertex y, and then we start adding x. So next we take the vertex y plus x, then we take the vertex y plus 2x, and so on. And in the end, we added s k minus 1 times, and then we go back. So we have a sign. Right, so we add this copy, and let me give it a name. Just call it C of x and y. So this is the construction, and now we want to understand how it works. I'm going to say because these copies are actually done. So frame the copies CXY over all X is S, Y and N are actually done. In fact, even stronger, the vertex set of CX1, Y1, and CX2, Y2. So this vertex set, they can intersect at most one vertex. So in particular, they cannot share anything. Okay, so why is that true? So is it true? Otherwise, so suppose that they intersect in two vertices, so they share a vertex in some set Bi and also in some other set Bj. Right? So otherwise, there exists some I and j in one case, such that y plus I minus 1, y1 plus I minus 1, x1 is equal to y2 plus I minus 1, x2, and also the same for j. Means that this is what it means that those two copies share a vertex Bi and in Bj. But now this is a system of equations. So from here you can solve the matrix 1 I minus 1 j minus 1. This is invertible, so you can. So if x1 y1 has the same image under the matrix as x y2, then there is. And so this implies that x1 is equal to x2 and y1. So another way of saying this is that if I give you such a copy and I give you two vertices of this copy, then you can solve for S. Okay. This is the first property. Saying that can you show is that those are all the copies. There's no other. So those are all those. There's no other. So every copy of CK is equal to CXY or some X. Okay, so suppose we have a copy of the CK. So the first thing we need to observe is that every copy of CK is of the form B1 up to pk, or di in di. The first claim is that the only way you can have copies of pk is if how we expect, right? So we start here, and then we go, and then at the end. The first claim is that we can only have copies like this. And this is a place where we use the k is odd. So here, very important, the k is odd, because if k is even, this is not true. So you can have copies of C4, for example, that go like. Now, I will not prove this sentence, so you can think about it. It's not difficult to convince yourself it's true. So one way of saying this is that there is no homomorphism or ism of K who proper subset. Now, if you know what this means, then great. If not, then we will talk about homomorphism very soon. You will know. But this is a way to explain why this happens. Okay. So now suppose we have a copy like this. So okay, so we have B1, B2, 3, and so on up to K. Now we have to think about what the construction is like. So why is there an edge here between B1 and B2? Well, it's only possible that to have an edge here if B2 is equal to B1 plus some edge. And let's call it X1. And same thing here, it's only possible to have this edge if here it's plus some X2. And so on and so forth. At the end, this is plus some xk minus 1. Finally, we have this edge, and the reason we have this edge is because this is plus some k minus 1 times some other x, which I'm going to call. Okay, so this is the only way we can have edges. Okay, and now finally we use the property of x. So so what we get from here is x1 plus xk minus 1 is equal to k minus 1 times k. Right? But remember that those x's come from n. So the only way for this to happen is that all of them are equal. So because of the choice of s, that means that all of them are equal. So let's call this number x. So what this means is that actually V1 up to Vk is equal to the copy P x1 or y x1. Okay, so the only copies we can have are the original copies. And this proves this. Any questions? for all cycles, we proved that the removal lemma is not polynomial. And now we want to do it for any graph which is not cycle. So it's some non-bipartite graph. And of course, we want to use that H has one cycle. So suppose that P of H is 1 up to H, and also that 1 up to K, and 1 is an odd cycle. Right. So we can try to do something similar to what we just did for all cycles. Namely, so actually before I continue, there's one, before I continue for general age, there's one remark that I want to make, is that this construction, the construction we just saw, this is by, the idea for this construction is by Russell and Temeretti. Together with the triangle removal lemma, implies Roth theorem. Theorem S is a subset of 1 up to S, and S has no three-term arithmetic progression, then S is sublinear, so it cannot have sign linearly. So let's see this. So the point here is that we have this construction that started from not written anymore, but we started from this set F. It doesn't have a solution to this equation, and we saw that the special case of this equation is a three-term arithmetic progression. So the special case is x1 plus x2 is 2 times x. So what we did now, we took a construction of such a set, and we used it to prove hardness for the removal lemma, but you can also go the other way around. You can use the construction and the removal lemma to prove that these sets cannot be too large. So they can be almost linear. They can be n to the 1 minus 1, but they cannot be linear. So let me show you the proof of this. So in other words, so let me just reformulate the theorem. For every epsilon, there exists some n0 such as if n is a fixed n0, then S is size at most epsilon. Right, so what I wrote down is just what it means to be linear. So let's prove this. In the construction, where the graph is n times s, disjoint triangles, and also no other. Those. Right, this is what the construction gives us. Now we can apply the removal lemma. Let's suppose that S is at least epsilon n, and show that n is small. And so by the removal lemma, so if S is at least epsilon n, then we have here epsilon n squared, disjoint triangles. Right? So by the removal lemma, the number of triangles in G is at least delta n cubed. That's what the removal lemma is saying. But on the other hand, the construction has no other triangle other than those. So in particular, all the triangles are edge disjoint, so we cannot have more than n. Right, so if we solve this, we see that n is at most 1/10. So this means that, so delta is the delta from the removal lemma. So as soon as delta K3 our notation, so as soon as n is bigger than this quantity, then it's impossible to have at least epsilon. Right, so that proves. So that's what this means. So what this proof is that n0 at most, we already know that in the removal lemma, the dependencies are of tower type. If I take the best thing we know, so this is the results of Fox that I mentioned yesterday. Then we get this bound. Right, so what this means is that, so if I translate it, it means that S is something like most n over log star n, where the log star is the inverse of the tower function. I think with the log here, it should actually be n over e to the log star n. This doesn't make sense, right? So this is a very, very slowly growing function. So this function, what's telling you is what height of tower do you need to take to reach n? So how many times do you need to do so that you get n? Right, so this is a very slowly growing function. And so in this one, so this proves Roth's theorem, but actually with a quite weak bound. And for this problem, unlike the triangle removal lemma, there are much better bounds. So, this is beyond the scope of this course. If you're interested, you can read it up on it. of the best bound Cardinals break for Kelly and Mecca. So very recent, 100 years ago, that S is the most n over e to the log n somehow. So that was a remark about the connection to Ross theorem. So let's go back to a general graph A. So we want to find a similar construction for a general graph A, and we can try something similar. So what we can try is we take set V1 up to V2, V3, and so on, up to H. So now H has 8 vertices. So we take set, and what we can try is for every, here's the first attempt. For every x in our set S. So this construction always works by taking some set S with no solutions to some later, then it's and y in n. We can put a copy of H on V1 up to VH, where VI is in VI, and it's equal to y plus I minus y times x. Right, so I'm trying exactly the same thing. So I will take here the vertex y, here the vertex y plus x, and so on. And I'll put a copy of H. So this is what we did for an odd cycle, and I'm trying to do this for general. So the issue that we might have is that we don't know how the copies of H look. Right? So earlier, what was really good for us is that every odd cycle actually must look this way. But for general H, maybe we don't know it. So if we did know that every copy of H looks this way, then in particular, because on the first, so up to VK, y plus k minus y. So on the first k vertices, we have an odd cycle, because we assume that the first k vertices of H make odd cycle. So if we knew that every copy of H looks like this, we would know that every one of them contains an odd cycle like this. But we know exactly that the odd cycles here are only those that we put in. So we would have good control of the copies in this good one. So the only thing that is not clear is why all the copies of H like we want. So in order to handle this, there is a nice notion that's called for. So let me define this, and we'll see how this works. So first I need to define a graph homomorphism. So who has seen the definition of graph homomorphisms? Okay. from G to H, so G and H are graph. The function is a map phi from G, the vertices of G, the vertices of H, and this map preserves edge. So for every edge x, y, and g, the image of the edge, phi of x, phi of y, is an edge of H. So this is the definition of correspond. It's a map between the vertices that preserves J. And second definition that we need, the following, so the core is the minimum subgraph of H so here minimum, I mean in terms of number of vertices, number of vertices the minimum subgraph, let's call it K, such that H has a homomorphism to K. So I'll use this notation with the arrow. So this means that there exists a homomorphism from H. So let's see why this definition is. Well, let's practice the definition code. So what happens if H is bipartite? So can someone tell me what the core of H is? Fine. And another example is that this case for an odd cycle, core of pk, then it's a cycle. So there is no homomorphism. So every proper subgraph of pk is bipartite. There's no homomorphism. So the minimum subgraph to which there is homomorphism is pk. Okay. Now the key property you're going to use is that, so let's say be the core of H. So every homomorphism from K to K is an isomorphism. So I claim that to take the core of the graph, then this K has the property that any homomorphism from K to itself has to be an item. So let's prove this. Now, if P, if phi is not, if the image of phi is not the whole vertex set, so if it shrinks, so we get the contradiction. So why do we get the contradiction? Then take a homomorphism, call it phi, from H to K. So we know that there is a homomorphism from H to K. Now, if I take psi and then I apply phi on it, then this is a homomorphism from H to a proper subgraph of K. Okay, and this is in contradiction to the minimality. Okay. Okay, so if I take any homomorphism from K to K, it has to be bijective. It has to, right? Because the image has to be everything, therefore it has to be bijection. But because it also preserves the edges, it has to be a isomer. Okay, very good. So this is the important property of the coordinate movement. One thing you could have asked is why I write that here. So why do I claim? Looks like I claim there is only one such graph. So this is true in some sense, in the sense that they are all isomorphic. So after isomorphism, there is only one for. Let me write this, and I leave it for you as an exercise. If you're interested. Four is unique. If K1 and K2 are cores of H, then they are isomorphic. Way you prove it is similar. Question so far? Okay. So now we can finally prove the theorem of Alon. Let me say it one more time. So if H is not bipartite, then the base of H in the removal lemma is polynomial, so it's smaller than anything. So for the proof, we take we consider the core of H. Now we have two steps. First, we prove the theorem for K. And then we use this proof it for H. So let me start one. basically exactly what we were doing, right? So it's exactly this. Let me. Okay. So let's suppose that the vertices of K are one of P, and that's one up to K in those cycles. Then we just do what's written here, right? Nice one. So for every X in N, Y in N, whose copy of K is K and Y, K on P1 up to P, where Pi is in Pi equals Y plus I minus 1. So it's exactly the same construction as we had for us. And now, we need to show that this works. So the first thing that we can show is that the copies are edge joints. And this is exactly like we had before. And the second thing is that we want to estimate how many copies we have in total. Right? We want to say that we have many edge joint copies, but on the other hand, we have few copies in total. Now, and here the key thing to observe. So if I denote this graph by G, and G, the G is homomorphic to K. So can someone tell me why G is homomorphic to K? Yeah, okay. So the homomorphism just maps the I to I. So this is the homomorphism. And therefore, every copy K in G corresponds to a homomorphism K to K. Because if I have a copy somewhere in G and I take this homomorphism and I restrict it to the copy, then I get a homomorphism for K. But we know that this has to be an isomorphism. And therefore, this means that every copy of K actually looks like. So this implies, so because every K to K homomorphism actually an isomorphism. So this implies that every copy of K is form P1 P, where Pi is in Pi, and also Pi is vector of I. Every copy is exactly like we expect, And therefore, in particular, this means that for every k copy, B1 up to Bp, the first k vertices, so B1 up to Bk, is an odd cycle. Now we can use this to count how many copies of K we have. So the number of odd cycles, C1 up to Bk, is the smallest n squared. So this we already saw. So we saw when we proved it for odd cycles that we only have the odd cycles that we put in the construction, right? We don't have any others. And they're all edge disjoint, so there is most n squared of them. So this means that the number of copies of K is the smallest n squared. And so this is the number of ways to choose the odd cycle. And then we need to choose the other vertices. And we have at most this many options, right? Because we have to choose P minus K vertices. So then we have at most n choices per vertex. So we have this bound. And then we can just write that this is n to the, this is at most n to the P minus 1, right? Because K is at least 3, which is n to the P over n. The usual thing we do, and this is at most epsilon to omega of 1, then to the P. And because we know that m is at least 1 over epsilon to omega of 1. What we're saying is that because we have few options for the odd cycle, then we can just use the trivial bound for the rest of the vertices. Okay, so this proves the theorem for core. Now the question is, what do we do for a general H? So to go from K to H, we just blow up this construction by a constant factor. So let's say to be on the safe side, by a factor of the number of vertices of H. So why are we doing this? Well, K is homomorphic. Sorry, H is homomorphic to K. Right. So if this is K, this is K, then there is a homomorphism from H to K. And now, if we look at the 3 images of the vertices, then that means that we have a partition of H according to the 3 images. So just, you know, if there is no edge here between these 2 vertices, then there can be no edge. So in other words, if K is 5 cycles, then H is contained in a blow-up of 5 cycles. So the point is that H is contained in a blow-up. So this is equivalent to saying that H is homomorphic. So if we take this construction and we blow it up by a constant factor, so large enough so that we get a copy of H, then the copies of K we have become copies of H. So we can show that we have many H-disjoint copies of H. On the other hand, we know that K is a subgraph of H. So every copy of H must contain a copy of K. And we have an upper bound on those, so we can get an upper bound. So that was very quick, but the point is that we take a log and you can show that this works. And in the lecture notes, I think I have a bit more detail. Any questions for this? Yes. So in order to upper bound how many copies of X you have, you can just upper bound how many copies of K you have. And each of these has to come from a copy of K for the draw. Because it's still homomorphic to K, even after you draw it. What's make it the core fit? Yeah, maybe. More questions? Something that the teacher has we are not the number of codes. We cannot say for the code. It is not that the subpage dominate the other subpage. You're right. Yes, you're right. You can say that the number of homomorphisms from H to the graph is also small, because you're right that the injective homomorphism dominates. Does that answer your question? Yeah. More questions? Okay. So I want to end with a remark. Remark, and then I'll tell you a problem. I want to mention what problem as I know. First remark is that everything we were doing generalizes to hypergraph. Well, there is the hypergraph removal lemma. Statement is exactly the same. For every hypergraph, for every K uniform hypergraph H, and for every epsilon, there is this one delta of H, epsilon, that if G is epsilon par H3, then G has the delta and the V of H goes to H. Now, the only thing we have to adapt is what it means to be epsilon par. So that means that we must delete the epsilon and the K. So now the uniformity is K and to the K edges to make H3. Okay, so this is the removal lemma, and this was proved. This was proved by Gowers and independently by Nagel, Vedel, Van and Schaff. The big deal actually, because in order to prove this, they had to figure out a way of generalizing the semi-ready regularity lemma hypergraph. And it's not a straightforward generalization. So actually, regularity for hypergraph is much more complicated than graphs. If you're interested, again, you read up on this. I wanted to talk about this at some point. Okay, in this summer school, I don't know if we'll have time. Maybe we'll have time towards the end. So this is one thing. And the second thing is that Alon's theorem that we had previously is also generalized to hypergraphs. So the theorem of myself theorem. And this is the delta of S delta epsilon is polynomial in epsilon. And it's an only H K per time. So K partize means that you have a partition in K set, P1 up to K, and for every edge intersects all this. The correct generalization of bipartite. Okay, so this is about hypergraphs. And last thing I want to mention a problem. The problem is about ordered graphs. Maybe you've seen already ordered graphs. So ordered graph is just a graph where you have a vertex ordering. Okay, so everything remains the same, except that when we talk about copies of a graph, the copies have to respect the vertex order. Right, so for example, these two graphs, they are isomorphic as unordered graphs, but they are not isomorphic as ordered graphs. They're different orders, right? Because each of them is a path of length 2, but the order matches. And the problem is to prove a polynomial, remove a lemma, or ordered forest. So let me check exactly what it means. So if S is an ordered forest, so it's just a forest with some ordering. G has epsilon n where S is joint copies of S. Then G has poly epsilon times n to the p of S copies of S. So if you could prove this, we would get a characterization for ordered graphs of when the removal lemma is polynomial. So the conjecture we had in a paper with Tomon is that this is polynomial if and only right H is an order homomorphic just briefly, order homomorphic means that there is a homomorphism that also preserves the order. It's not really important just want to give you the full picture. So our conjecture is that polynomial if and only if H is order homomorphic to a forest. And to prove this conjecture, you just have to prove this statement. So we know the other direction. We know, so this implies, this is for forest. This would imply if H is order homomorphic to a forest. And right. And the other direction we know. It's not order homomorphic to a forest. We know it's not.
Do you need to preserve in a homomorphism the order of every character?
Yeah, so basically you split into the pre-images are integers.
Okay.
I have a question that it said that in a Lewis result, it's down that H is polynomial and moving by complex. Why here we conjecture that it's order forest? Is the order right?
Well, because the order, so ordered graphs behave a bit differently then. So if you know a bit extremal graph theory, then so another theorem about bipartite graphs is that bipartite graphs are the only ones that have vanishing true-undensities, right? They're the only ones that have true-undensity 0. Now, for ordered graphs, it's not true that if and only if the graph is bipartite. For example, this graph is bipartite. It doesn't have vanishing true-undensity because you can take a complete bipartite graph where this interval is before this interval, and this will avoid that. So actually, the correct analog is that something called the interval chromatic number, which is the number of intervals you can split into, giving you a coloring. So then it is true. So for extremal graph theory, it's true that the density is vanishing. So it doesn't exactly answer your question, maybe, but just I want to say that for ordered graphs, it's different. It behaves differently than other. More questions? Yeah, the actual answer is that if it contains any type of structure. Yeah. More questions? Okay, so tomorrow we will talk about induced removal lemma. So we will try to generalize this or extend the removal lemma to the induced set. So instead of subgraphs, we hear about induced subgraphs, and we'll see that we need some new ideas to prove such statements. And we will also at some point start talking about PC dimension. So PC dimension plays a role here because it gives us small regular partitions, and we can use it to prove removal lemma.